Greetings. In this one, we will talk about virtual work. And virtual work is used in order to determine some values in some systems. And precisely in this case, I will be considering via virtual work very small displacements and applying them in the context of work, where work is force times distance, which is a very important principle to know. This is switch side, but doesn't matter. Which is a very important principle to know even before starting, because virtual work, how I will use it, will basically mean that I add up all the works where each force times its distance traveled, and the addition of all of them should equal to 0, because there's statics, and we will use this principle in order to solve an example. So basically, that's the idea. Not going into too many details, although in some future videos you might get more into details and perhaps take another example and so on. The example I'm doing in this case involves some beam that's attached, rigidly attached, or rotation is allowed, but it's attached such that it doesn't translate on this end. And that beam is attached to this pin on which it can rotate, and no friction of that pin is taken into account because that would be too much work to put inside this example already. For slight simplification, let's say there's very good, there's no friction caused by the joint, and so it rotates freely. And then there's some forces applied to the beam, because of which it's not in this default position as one would expect, just hanging down like this, but it's actually to the side of it. And the reason is, by the way, the beam has a weight. I will add that as a component of our calculations by itself. So the beam by itself is not set to be 0 weight for simplifications. Actually, in this case, it does have some weight. And also it has some determined length. But I will work with all these things as parameters. Also, we could take concrete numbers, but in this case, you will work with it as parameters. In the end, we can look at concrete number put inside the result. So what I have is this beam, and the beam has weight W. That means already I'm not given the mass exactly or the acceleration, although I might expect this is on Earth with acceleration of something under 10 newtons per kilogram. In any case, the weight force, the force caused by the mass, and by the way, the beam is homogeneous in weight, is distributed equally across all its parts. Therefore, I can take the centroid, and we're looking at it like 2D, so I take the centroid, and the weight force representing the weight of the beam itself, pulling itself down, is going to be an arrow from that centroid going straight down, called W. And then we have some two forces at the tip of the beam, which first of them is going to be G going down, and then we have F. So the more default X direction, F this direction, and X, and G this direction. And then also we can also somehow call the angle at which the beam is hanging compared to the default scenario. So normally it would be this, but it's pulled to this side, and so this angle here I will call theta. And the length of the beam, which is basically from this side to this side, is gonna be, let me say that for simplifications, I really mean the very tip of the beam here. I also mean the very tip of the beam for the joint, and the length of the beam is gonna be, and the width of the beam is negligible, although it's drawn quite wide. Let's say that's not really part of the calculation. And then the length of the beam, well, for length we might use L. So length of the beam will be L. And so the beam has some length, is hanging to this side because this force F pulls it, but also that's repelled by this G pulling it back down, and this W weight of the beam itself also pulling it back down. And now I want to know what is the equilibrium situation of this angle. So if we have some force pulling this in this direction to the left in X, down in Y, and then this weight down, which, because it's on the centroid of this homogeneous body beam, is applied or drawn as a single force, the whole weight of the beam in the middle is pulling also down. So in relation to these, what will be the angle at which the thing is in equilibrium? And so we will use this virtual work here, and because this is a static scenario, the virtual work, so total work will be 0 in addition in result. And that's the idea we're going to be using. So basically, what I'm going to do is, first of all, I've already defined what is work. It's force times distance. And now I'm going to express distances in this object, especially the ones that are changing. So a distance basically of, I'm going to say that this is like the reference point, this is 0. And although it's drawn like not at the tip, let's say that the joint is really much at the tip of the beam on the upper tip here, where it's on which it's rotating and on which it's hanging. And I want to see what is this angle, and I'm just going to use the virtual work the way that I know the default position would be if it was hanging down, but we had the position as we have it. And I can express that in some y coordinate and x coordinate. And what I'm going to be using here is, I'm going to say that my reference point is kind of thinking about it the way that my reference point is here. And so the y goes down like this, and then the x goes down like this, goes to the left like this. So it all goes from the hanging point till the tip, which is the one that is translating in space because it's at the tip of this beam. And so we will calculate directly, we will express directly this x and y in a way such that we will know how far is the point of application of f of g vertically from this initial point, how far is the point of application of f horizontally from its default value, and then I will find a differential of these expressions, because these expressions I just mentioned will be in terms of cosines and sines and functions, and then I'm going to take a differential of them, and that differential is going to be what we're going to use for the virtual work as the distance. And the differential of that distance we will multiply by that respective force to which it's connected. Everything will be added up and everything will be equal to 0. And then a lot of things will cancel out on both sides, and from that directly we'll get the result. So let's see how it's done in concrete practice. So I know this is L and there's this angle theta. So Y can be expressed as L times the cosine of theta. So it's L times cosine of theta. And then X can be expressed, and by the way, I will put this y at the tip because this default y, so this y is going from here all the way to here, so I'll call this y, and there's the L cosine theta, because it's the projection onto this line, onto this vertical line from the L. That's to the side now. And then also this is going to be used for our g, because g is pulling it down kind of, and we know how far vertically it's already located. When this is our initial point, we're going down here. And we also need an expression for how much vertically down is w, because w is also in the same direction like g. So we want in the direction in which it's acting, so in this direction how far from the initial point it is. So I'm also going to do, so I can call this y, I'm going to do like parentheses of for the g, and then I'm going to do another y, which is halfway, because the w is halfway. And by the way, that's a geometric property. When we have the weight in the middle of the linear beam, then if it's even hanging, still, if we look at the vertical reference, in 50% of this height, we're also still going to hit the centroid, the middle of a homogeneous beam in this case. If it's homogeneous, then the centroid is in the middle like this. Alright, and so this thing going from here to here kind of is going to be y of the w. And what is it going to be? It's going to be the same, but it's going to be half of it. Why? Is because we're considering this segment of the L and applying cosine theta to get this projection, this distance. So what I wanted to see is, because w goes vertically down, I wanted to see distance at which w in this image, in the general case, is in respect to L and the angle theta from this origin. And then I'm going to do the same for F. So I want X. And because we drew it in a way that it's hanging to the left, I can also like create an arrow to show that I'm looking in this direction, but I can just leave that out. And what I'm gonna say is, I can still draw it here, perhaps. The x is gonna equal to, now, very similar. I will use L, but I need this horizontal distance. So it's the distance horizontal from the origin, from the reference point to the horizontal distance where F has the point of action. And then it's gonna be L times, oh, it's already here. L times sine of theta. It's this length. So this is perhaps the most hard part, the hardest part, because it involves looking at the geometry. And this example is still simple. There might be some examples that involve even more looking into it, because one can make a lot of mistakes in this context already. But in any case, okay, let's continue, and hopefully there are no mistakes. But once again, this is one of the hardest parts, perhaps the hardest part, to identify these distances. And now that we've identified that, note that they are functions of the length of the beam, which is going to be constant, and this angle. That's kind of variable, because the angle will change, and we'll see in the end, depending on the magnitude of these forces. So that's also why in the end I can put something for the Fg and W and change the theta by. But therefore, because theta is kind of the variable here, this thing, the x is a function of theta at the end of the day, and y of w is a function of theta as well as y of g. They're all kind of functions of theta. Alright, so here I have y of w, y of g, this could be called x of f, but as you see, for which forces did I look? Well, I have these forces that cause this deviation from the original position and direction of the beam hanging. But these are precisely the forces for which, these are precisely the forces to which I'm looking for the distance from the original point, because we're gonna monitor a small change. We're gonna look at the small change, or the differential of this in respect to the angle change, and then we're going to put it in context of the whole work. So now we have this. So we have expressions for all three forces that cause the deflection from the original hanging. We have their distances in terms of x and y coordinates, where they're a little peculiar because they point down and to the left. And that's kind of what happened, because our forces are pointing down and to the left. So that's the reason for that choice. And now that we've gotten that out of the way, we have x and y, and also this half y because of this w not applied at the end but in the middle. I can start taking the differentials. And the way one takes differentials is it's a little harder once there's something like a total differential for a multivariable case, and so one has to add it, although it's the same idea, but the process is a little longer and one has to follow the rules a little stricter and make sure there's perhaps less space for some alternative ways of doing it. But in any case, I'm going to do it now as is most analogical in context of derivatives. So, as I said, y, and by the way, this might be confusing. I will put it as a subscript because it might seem like it's a function of w, but it's not really. So it's connected to it, and for the x I can say it's sub f because it's connected to it. Although for x there's no other x, so therefore I didn't have to differentiate with an index. So with y I had to put this g and w because there's two y's. But for x there was just one x, so I call it that. All call it x. Now we named it with some index of f, but it doesn't really matter. Okay, so now we have these three things, and I want to know what is the differential. So basically, this is the distance, but there might be some small differential dx in this sense, and then some in this direction there is dy. So from these forces, because this dx is actually gonna cause this point to go to the left, but also because of this being strictly attached, is also going to cause this point to translate up as that happens, right? And then this dy, although the motion in reality is towards the left side, as it goes further out from the original position, the dy should be up, right? But not because these functions or these forces act on it in a way that they reverse that motion originally. But in any case, let's continue now. So this might already look like a complicated and confusing example, but we can just write out the three distances that were identified. So y sub w, y sub g, and x sub f. These are one-to-one for each of the forces we have. Their distance from the reference point here. And so, y sub w is this, and so on. So, L over 2 cosine theta. And then y sub g, L cosine theta. And x sub f is L sine theta. And now I want to find the differential. And the way I take a differential is by differentiating both sides in respect to theta. So, you might end up rewriting this a few times more because there's going to be some calculations involved. In any case, in respect to theta, I have y sub w over, well, basically, dy sub w over d theta is minus L over 2 sine theta. And then both sides, I want the differential dy, so, or dy w in this case, to be more concrete. So therefore, dy w, I multiply both sides by the d theta, I get the d theta on the right side. Although that's not really important, especially in this case, every d theta will be cancelled out with 0 on the other side of the equation anyway. So we write it, but we'll get rid of it in a second anyway. And then y sub g, again the same idea. So the derivative in respect to theta on both sides of this equation. So this is minus L sine theta. And again, multiply by d theta on the right side. So dy sub g equals minus L sine theta d theta. And then the third one is L cosine theta. But I will already write the result because we have already seen the pattern here. The differential is going to be dx sub f, and it's going to equal to the derivative times d theta. Alright. So these are the three differentials we got. And now these differentials are going to be the distances, as would be distances with standard work calculations. Like there's f times s, so the s is going to be these three. And for the f, we have to use the respective forces. Add it all up and set that all equal to 0. And that's our equation we're going to directly use for the solution. And now we're very close to the solution. So that's the point. We got these things. I mean, we can delete this kind of and only keep the differentials written down to have space. And so I'll write it more to the right. And so these are our three differentials. And I said our total work is 0 and it will be equal to each of these respectively multiplied by their respective force. And then it's everything's gonna work together eventually. So dy, so the small change in y, or differential of the distance y for the weight w. So it's gonna be the force itself times the change in displacement it causes, sine theta, d theta. I'm gonna write even the d theta, but we'll see in the end the d theta will cancel with the 0 anyway. We'll divide both sides by d theta. Then we have plus, so we have this first one plus the other plus the function g. So we have these three forces, w, g, f. So then g times its differential, and that's going to be minus L sine theta d theta. And then plus the third one, which is f, times its differential, L cosine theta d theta. So these three. And now that we have that, we can cancel out the theta on both sides. So this, and this. And then we can add the ones that have a minus sign to the left side, perhaps. And from there, we can directly start manipulating this equation. So we'll end up with this. And now I can isolate the sine theta. So you see, these are still the weight force, this is the length of the beam, and this is just divided by 2. And then this is one of the forces, this is the G here, so we still see the connections directly. All of it equals to FL cosine theta. And now we can generate a tangent out of this equation by dividing both sides by cosine, and I will also divide both sides by this parentheses. So from it, the semi-final result will be tangent theta equals to FL over WL over 2 plus GL. And now I can divide the numerator and denominator by L. This. And that actually kind of makes sense because the beams, because we see it's homogeneous material, its centroid is in the very middle, and the weight is applied in the middle of the length of the beam, and so the length won't have an impact on the result actually. So our equilibrium value of the angle at which it has to hang will not be dependent on L, which is interesting. It cancels in numerator and denominator. So this over W over 2 plus G. And now we can modify it a little further. And so this is sort of calculation, but in the end we have some interesting results. So just a second more and we'll be there. Tangent theta Alright, so we have the value of theta in respect to the three forces involved. So this is our result. And also it makes sense because these three forces, well, it's all positive here. And yes, we're gonna give their positive values and that's gonna go into arctangent. So that's doable. And so we have an expression for the value of theta from this. So this is what we got. It might seem more complicated from the image, and it really is in the end of the day, because there's a lot of things to keep in mind. But at the end of the day, what we really have to do is identify the forces that cause this movement, and those were these. And we see it's okay, so it's leaning in this direction. So F is pulling it to the left, G is pulling it back down, and W is also pulling it back down, kind of. And so from that we derive also some values for this. Because W is vertical, we look for its vertical distance from here. Because G is vertical, we look for its vertical distance, F is horizontal, we look for its horizontal distance. And by their respective distances that are coordinate-wise related to their respective directions, and that's also why it's very practical that we have perpendicular forces. We have just two directions to take care of. So that's a nice thing for an introductory example. And thereby, you see, even though they're not all in the same direction, we could add the product of force that's vertical times its vertical distance plus a horizontal force times the horizontal distance, and it's all adding up to 0. And so at the end of the day, even if we were just adding the horizontal ones, they should also add to 0. And so the horizontal works. And then the vertical will add to 0, so we might as well just add the two zeros, and on the other side add the two component groups. So at the end of the day, we got this result. So what it means that we can have some F, W, and G, and see what the theta will be from that. Or if we want a particle theta, then one might choose some F, W, and G for that.